Hey, howdy, space nerds. Are you liking this podcast so far? Well, Are We There Yet is supported by listeners just like you. So consider showing your support with a financial contribution to WMFE. You can do that by visiting WMFE.org/support. Your gift helps us better explore exploration. Now, let's get to space. From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast that asks the question, are we there yet? Hi, I'm Brendan Byrne. At the Kennedy Space Center, there's a group of scientists and engineers that think outside the box when it comes to building the tools that will one day take us to Mars. I'm calling them the Renegades of research and development, but they call themselves swampworks. One of the biggest challenges in space exploration is fuel. It's kind of important, right? But it's also really heavy. And we'll need fuel to get astronauts back from Mars. That means we've got to pack extra fuel. That takes more fuel to send the fuel. It gets crazy. But what if we can make fuel when we get there? Now, the term scientists use for that is in situ resource utilization, or in situ for short. I met some of the folks at Swampworks to find out their crazy, out-of-the-box plans for exploring places like Mars.
Okay, my name is Rob Mueller. I'm the senior technologist and co-founder of the NASA Kennedy Space Center Swampworks.
What are some of the things that you do here at Swampworks?
Swampworks develops new technologies for space exploration, and mostly they're tied to resource utilization. So there's plenty of resources in outer space. The trick is that we have to develop new technologies to harness those resources, and that's what this lab tries to do.
Because one of the challenges with exploring these distant bodies and planets is energy and fuel and resources. You don't want to bring it all with you, so you're trying to see if you can find it when you get there, right?
Yeah, regardless of the cost of space transportation, it's still a giant logistics problem. So we can only go to Mars every 26 months. So even if you had all the money in the world and all the rockets in the world, the laws of physics still say you can only go every 26 months. So imagine you're sitting on the surface of Mars waiting for the supply ship. But Mother Nature doesn't let you bring the supplies until the next opportunity, which is on 26-month intervals. So this is a problem. So if you want to survive on Mars, you really need to be self-sufficient. And to be self-sufficient, you have to do what the pioneers did and use local resources. But to use the local resources, you need to develop the tools to use the local resources. And that's what we do.
Now, this is a huge space with all sorts of cool things I'm looking around. Is there anything in particular you want to show me while we're here?
Yeah, we have an overarching vision, which we call dust to thrust. And dust to thrust means you collect dust, which is soil or regolith in technical terms, and you process it all the way to the point where it goes into a rocket engine and it provides thrust. Now, the reason this is important is that in our current Mars architecture at NASA, in order for the astronauts to come home, they have to load the Mars ascent vehicle with propellants that are made on Mars. So unless you can make those propellants on Mars, you are not coming home. So that's why this dust to thrust vision is important. And we've developed a series of technologies that link all the different components of dust to thrust so that you can get from dust to thrust. And I'd like to show you what those components are.
Let's see.
Okay. So it starts with the dust. So we have a large bin, which we call the big bin.
You say bin. This probably is more square footage than my house is. This is
okay.
big.
It's 25 by 25 square feet. So
okay.
It's 25 by 25. And it's about 3 feet deep. And it has walls around it, and it has an enclosure, a transparent enclosure. And it's filled with this very fine basalt dust. It's moon dirt is what it is, and it's crushed basalt. And the particles are between 20 and 100 microns in size, and some are below 20, but the majority are between 20 and 100 microns in size. So that's kind of like talcum powder. It's like crushed glass that's the size of talcum powder. So imagine that. And there's 125 tons in this bin of this crushed rock, this crushed basalt rock, which we went to Arizona and trucked it in from Arizona, from a volcanic region near Flagstaff, Arizona, which happens to be the exact same mineralogy as what you find on the moon. And we call this a lunar regolith simulant. So we have a big bin that's filled with 125 tons of dirt. That's where it starts. Most of the resources are in the dirt or in the atmosphere or come as energy from the sun. Those are the variables we have to play with. Those are the resources we have. For us, it starts with two things, the Mars atmosphere and the Mars regolith. The Mars atmosphere is 95.5% carbon dioxide, so we can acquire the carbon dioxide, we can compress it or freeze it, and then we can extract the oxygen from the carbon dioxide. And that means we have a carbon left over, a carbon molecule. So if we get water, hydrogen, we can get hydrogen out of the water, combine the hydrogen with the carbon to make CH4, which is methane. So now we have oxygen and methane, which is the fuel, the oxidizer, and the fuel for a propulsion system propellant. And that's our goal. So the first step then is to dig up this dirt on Mars or the Moon. It can be done at either destination. It can even be done on an asteroid. And then you have to extract the resources out of the dirt. But in order to do that, this will not be done by an astronaut with a shovel. It will be a robot doing it. And the robot can't look like a big yellow construction machine that we have here on Earth. It's too big, too heavy. So we have to reinvent digging, reinvent how we would do that. And we have a robot that we've developed, which is small. It only weighs 60 kilograms, and it can dig enough material to make enough propellants for the Mars ascent vehicle to come home. So the first step is digging, and we have a robot that digs. It goes into this bin, and it digs up the regolith. Once it's acquired the regolith, it drives over to a regolith processing plant, when we have a mock-up in our lab here, and so we can test the technologies. So we bring the regolith over, we drive the excavator over from the simulated planetary surface, come over here to the resource processing plant, and we put it into a mechanical arm which filters out the rocks and then raises a bin, a hopper bin, up and transfers the filtered regolith where all the rocks have been size sorted and puts it into a dryer. And the dryer is simply a pressure vessel with a valve at the top and a valve at the bottom, and that closes off the pressure vessel. So now you can extract the water from the regolith simply by heating it up. By heating up the regolith, the water evaporates. Now you have vapor, and you condense that on a cold finger, and now you have liquid water. You clean up the liquid water, electrolyze it, and now you have hydrogen and oxygen. Meanwhile, another module at this processing plant called the atmospheric processing module, we have a mock-up of it over here, that's producing oxygen from carbon dioxide, and we use the Sabatier process, which means when you combine hydrogen with carbon dioxide, you get methane in the resulting reaction. And so now we have oxygen and methane, and we can, it comes out in gaseous form. You have to freeze that into a liquid form, then we store it as a liquid, which is called a cryogenic liquid, and then we use the cryogenic liquids in a rocket engine to provide thrust. Once you have thrust, you can come home. So on Mars, we need to have 30 tons of propellant in order to come home. You can either bring the propellant from Earth, or you can make it there. It's going to be a lot less transportation if we make it there.
So just to recap here, you're literally taking dirt and turning it into that oxygen and methane that you need for fuel in equipment that really isn't that big. Like, this is not very big, right? I expected to see this giant plant with all this stuff, but I mean, it's not much taller than me and not too big around, right?
It's not that big. For a Mars architecture for 4 astronauts, it will weigh 1,000 kilograms. 1 ton of equipment can produce enough propellant for the astronauts to come home.
What's kind of the biggest challenge you still need to work around with a system like this?
Well, obviously, if I told you, I'm going to drive your car for 5 years and you're not allowed to change the oil, check the pressure in the tires, and you can't even put gasoline in it. And by the way, there's no driver either. So how are you going to do that? So we have some severe challenges on operating equipment in extreme environments for a long lifetime and autonomously, which means there's nobody there. So those are the major challenges, is how do we get equipment to operate in these very extreme environments, and the communications delay can be up to 40 minutes to Mars, so you can't joystick operate it. There's no teleoperation possible at Mars. So these have to be autonomous machines. Those are all big challenges.
Are you borrowing some best practices from, say the Curiosity rovers or successful rovers in the past?
Sure, absolutely. We work with the JPL team, and we collaborate all the time with them, and they tell us what works and what doesn't work. In fact, the resource on Mars, the water resources we're looking for, MSL right now is doing those kind of investigations, and we learn from that. And we're constantly trying to learn from the data we have, including the orbiting assets at Mars, which are doing remote sensing, looking for hydrogen signatures. Where there's hydrogen, most likely it's water. So we're constantly trying to learn from what's being done.
Dust to thrust, really cool. I love it.
Yes.
Anything else, Ron?
That's the ISRU part of it. We do have other technologies in this lab as well.
Okay.
We try to do revolutionary technologies that have a large payback and not something incremental, but quantum leap effect. And so those are the kind of things we invest in. We take large risks, but it's all lab equipment. So if something fails, it's a cheap and quick failure, and we learn from it, and we fix it and move on. So it's very much a research and development mentality, and we're constantly pushing the envelope in this lab.
I mean, with NASA's ambitious goal to get to Mars in the 2030s, you're going to have to step up your game here, right? So you might see quite a bit of this stuff quickly developing into actual usable technology, right?
With the pace of technology development acceleration, it's not a linear curve. It's an exponential curve. So even though you think it's going slow, it's constantly accelerating, and all the technologies that are available are accelerating. So we think that we can accelerate the technology development. I'll give you an example. We have one project where we're 3D printing a habitat. So imagine building a house, and a large 3D printer shows up at the construction site and 3D prints the concrete structure for the house. Well, we don't want to launch bags of concrete into space when we have all this crushed rock in space. So we're going to use the local materials, the crushed rock, to make a space version of concrete, and then we'll use 3D printers that we bring into space, and we'll build structures like landing pads, roads, berms, habitats, large hangars. All these structures we can build in space using local materials out of space concrete. And by the way, that same technology can be used on Earth, so everybody benefits.
Cool stuff. Anything else you want to show me?
Yeah, we have a lot to show you.
Okay.
Let's talk about NIAC. NIAC is a program that NASA runs called the NASA Innovative Advanced Concepts. And this is for, if you think you're doing revolutionary work, NIAC is really revolutionary. It's going for technologies that have never, ever been conceived of, and that could have a dramatic difference to humanity. And so we do in our lab, we've been fortunate enough to win several of these NIAC proposals, which are hard to get. So I'd like to talk to you about some of the work we have going on here. The biggest challenge for landing on Mars right now is the entry, descent, and landing system. And we've all heard of the 7 minutes of terror, which is the Mars Science Lab had a system called the Sky Crane, but first it had to enter the Mars atmosphere. So the Mars atmosphere is a frustrating thing. It's there, so it heats up your spacecraft, but it's so thin that it actually doesn't help you slow down. So it's there, and it hurts you because it heats your spacecraft up, but it doesn't slow you down.
It doesn't help at all.
It helps a little bit, but not as much as it does on Earth. So we have to find new solutions. The very limit of the technology for entry, descent, and landing today at Mars is the Mars Science Lab Sky Crane system, which can land about 900 kilograms or approximately 1 ton of equipment on Mars. That's the payload capability. However, for the studies that we've done for human missions, they indicate we need 18 to 40 metric ton landers. So you have to scale up the current system at least 18 times, maybe as much as 40 times. So how do you land that much mass on Mars, which is required for a human mission? That's the challenge. We have a project that is trying to solve that challenge. It involves supersonic retropropulsion. So instead of trying to aerobrake in, we just brute force it with lots of propellant. So the laws of physics say that's possible. You just use lots of propellant. Need to slow down? Fire the engine harder. More thrust? Slow down. No problems. Where do you get the propellant from? You can bring it from Earth. You have a logistics problem.
It's a lot of propellant, right?
It's a lot of propellant. So where do you get the propellant from without having to bring it from Earth? So we had an inspiration where we realized that we can use this concept of in situ resource utilization, but instead of using it on a planetary surface, which is typically where we talk about pulling in the atmosphere into a machine that's situated on the surface of Mars.
Like dirt, right?
Like dirt or carbon dioxide atmosphere. Usually we would do it on the surface. The inspiration on this project was, why are we going into the gravity well to get the propellants, which we then have to bring up again in order to land using supersonic retropropulsion? So instead of going through the gravity well of Mars to the surface, why don't we scoop the atmosphere and make propellants on orbit, transfer it to a vehicle, and then use those massive amounts of propellant that we made on orbit to land the vehicle using supersonic retropropulsion. And that's the basic idea of this project.
Very cool. Very cool.
And I have a poster here showing that, and you can see that you come in and then you do aerobraking, which is exactly what we do today. But today in aerobraking, we simply heat up a shield and it ablates away. But instead of doing that, why don't we do something useful while we're aerobraking, which is scoop the atmosphere? You're coming through the atmosphere at very high speeds, and you can use a compression nozzle to compress the gas. Once you've compressed the gas, you can then make propellant from the gas and use it on orbit without ever going to the gravity well of Mars.
So cool.
That's
very neat.
That's one project we have. Another NIAC project we have is an interesting problem, because the resources on Earth's moon are at the poles, at the North Pole and South Pole. The water migrates to its thermodynamically most stable state, which means the lowest temperature it can find. At the poles of the moon, there are permanent shadows under the rims of the crater because the sun comes in at about 5 degrees off the horizon. So if you have a crater and there's a rim, it creates a permanent shadow. These shadows have been there for billions of years. So the resources, specifically the volatiles, which in our case the one we're most interested in is the water volatiles, they hop into these craters and they accumulate over billions of years in the craters. So we know there are water resources in the craters on the moon. But how do you access those craters? How do you process the regolith with the water in it? And how do you extract the water without some kind of energy form? You're sitting in the dark at 40 degrees Kelvin, 40 degrees above absolute zero. How do you do that? What we have here is a project that aims to reflect sunlight from the rim of the crater into the crater to power systems. It first of all gives you light so you can operate, and second of all you capture the light to create solar power, and then that solar power would power your processing plant and your mining operation inside dark depths of the crater. So you're deep inside a crater. This can be kilometers deep. Shackleton is 20 kilometers wide and kilometers deep. So you're in the bottom of the crater and you reflect light in. And this has a precedent. In Norway, there are small towns sitting in valleys that don't see a lot of light. So they put mirrors up on the mountaintop and they reflect light into the village in the valley. So it's not the first time somebody's tried this, but we'd like to do it in space on the moon. And so the next question is we need these giant reflectors. How do you do that? Well, what we have is we have these origami structures that are giant reflectors, and I'll show you one here. It's a origami structure that ploys out from a very small packaged envelope, and when it arrives on the moon, you deploy it out, and you have a large surface area of a mirrored mylar film that reflects light into the deep, dark shadows of the crater, which now lets you operate in the crater, extract the resources, and you can make propellants, drinking water, water for bathing, growing plants. Water is also a good radiation shield. So lots of things you can do with water in space. So this is another project that's very imaginative that uses these new technologies to create new solutions.
Mm-hmm. So using dirt, using origami, you guys are onto some pretty cool things here in SwampWorks, huh?
Well, we say life's short, play hard, and we want to change the universe.
Well, thank you very much for speaking with me, Rob.
Thank you.
That was Rob Mueller, Chief Technologist at Kennedy Space Center's SwampWorks. Now, making fuel is one thing, but finding the raw materials to make the fuel is another. Well, that's where these things called swarmies come in. As Kurt Lloyd explains, they're little robots that are programmed to act just like ants.
Swarmies are a set of small, inexpensive robots that are designed to go out and look for resources. For example, on Mars, you could send a swarm of small, inexpensive rovers to Mars rather than one really big, really expensive rover. And these guys are designed to act like ants. Scientists have studied ants, and they've figured out how they behave when they're out looking for food, and we've taken that behavior and we've put it into these robots, and it actually turns out it's actually a pretty simple behavior. You can reduce it down to just a small set of relatively simple rules, and so we've put these rules into these robots, and they go out and they look for resources. We just have them looking for barcodes, which you can see on the poster here. Mm-hmm. They go out and they look for the barcodes, and they bring the barcodes back home. They're pretending to bring resources back to the lander that dropped them off, and there's some really neat things that happen when you copy a biological system like an ant colony. The software on board these robots, as I said, is really pretty simple because the behaviors of the ants are really pretty simple, and so it doesn't require a huge onboard processor or a lot of memory on board. So you can accomplish these tasks of going out, finding resources, and bringing them home with simple, cheap electronics, simple, inexpensive robots, simple, also inexpensive sensors we're using. We think it's a system that could actually be useful on Mars someday to look for resources.
Tell me a little bit about it. Is this one of them? Am I looking at one of them right now?
Yeah, this is one of our swarmy robots. It has this version of the swarmy robot is not designed to operate on Mars. This is a demonstration project here on Earth, and so we're using sensors that make sense here on Earth. If this actually ever got picked up as a real project to go to Mars, it would look different.
And it's about, I'm looking at it, it's about the size of one of those RC cars you play with as a kid, right? Just maybe a little bit bigger?
Yeah, that's how we describe it. It's about the size of your RC car that you get your kids for Christmas, and it actually uses a lot of the same parts. All the parts that we use to build these robots, we bought online at hobby robot websites. So the hardware that make up these robots are basically just hobby robot hardware. There's nothing magic about the hardware, but what we've done with this project, we say that the magic is in the software. The way that we've designed these robots to act like ants and behave like ants, they actually communicate with each other like ants do, ants use a chemical pheromone trail, and they leave trails on the ground to tell the other ants that they're excited about something over there in that direction, and the other ants follow that. They get excited too, and they leave more pheromones because they're excited about whatever it is that's over there, and it's a natural way for the ants to communicate with each other without directly communicating with each other. Mm-hmm. You know, one ant can start a bunch of other ants on this trail, and without having to directly communicate with a lot of other ants. And so we've simulated that with this system, and we've got these robots indirectly communicating with the other robots by leaving a virtual pheromone trail with the lander, so that the other robots can come back to the lander and find out that there's a pheromone trail and go in that direction. On the video, you can actually see a computer simulation of the ants going out and finding food.
So they're not physically spraying anything, right?
They're not. They're simulating the pheromone trail, and there's a computer simulation.
Mm-hmm. You guys see the lines of code that it's going through, right?
Yeah, they're avoiding obstacles and they're returning home for a battery charge, which is something that ants don't do, but we added it to this system to make it something that could be used on a Mars mission.
So if you were to use a swarm of these, let's say you're looking for resources on Mars, how many would go into a swarm?
That's a good question. I guess it would depend on the area that you would want them to cover. We worked very closely with the University of New Mexico on this project, and they actually invented this ant-based algorithm for robots, And we took it and we extended on it and made it something that we added ISRU, Institute Resource Utilization aspects to it, so that it was closer to something that NASA might be able to use someday.
Gotcha.
And in their research, they have found that you can get a certain efficiency by putting a certain number of robots into a certain sized area. But if you try and put more robots in, they're not necessarily going to increase your efficiency that much. So they've run all the simulations and the calculations, and so we could go to them and say, we want to send a mission to Mars and we want to cover a 100 square mile area. How many robots do we need? And they'd be able to tell us a number.
Right?
Yeah.
What's you've got them here. I'm watching this video of these guys working, and it looks like you've got a little test chamber in here for it. What are some of the challenges you still have left with a system like this?
We would like to, if we got some more funding, we would like to kind of take it to the next level. This is a very entry-level project, and so if we took it to the next level, we might put some sensors on these robots that could look for water, for example, which is closer to a real mission that you would do on Mars, rather than just looking for barcodes. Another thing we're actually in the process of doing with the University of New Mexico is we're actually putting little robot gripper arms on the front of these robots. So instead of having the camera look for barcodes, we're going to actually have the robot look for these blocks and have the robot actually grab the blocks, picking them up, and carry them home, which is a little closer to a real mission where you're actually finding a resource and bringing it home. As far as challenges, every feature you add is a challenge. Obstacle detection, obstacle avoidance is always tough. Knowing where the robot is in 3D space is always tough. I mean, here on Earth we use GPS, global positioning satellites, to figure out where we are, X, Y, and Z coordinates. But on Mars we're not necessarily going to have GPS right away, maybe later, but so we would have to figure out a different way, use a different type of sensor to figure out where the robots were, and it might cost a lot more than a GPS sensor that we use here on Earth. So there's challenges there.
Kurt, thank you very much for taking the time.
Thanks a lot.
Well, that's going to do it for this episode. Rob Mueller, the technologist we met at the start of this episode, also runs a great space website. Visit outerspace.guru. It's a social site where users ask space-related questions, and this community of scientists answers those questions. So if you have any questions that I haven't been able to answer, well, why don't you go ask Rob and his friends? So check it out at outerspace.guru. Support for Are We There Yet comes from the listeners of WMFE. You can follow this show online. We're on Twitter at AWTYMars, or reach out to me in the Twitterverse. I'm at SpaceBrendan. And if you like the show, please leave a review on iTunes. That's how more people find out about the podcast. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. Find more space news online at WMFE.org/space. And until next time, I'm Brendan Byrne. Thanks for listening.